Okay, we will today take up the topic of analysis of single phase motors. In the last lecture, we reviewed the methods of starting of single phase motors, split phase motors, capacitor start motors, capacitor run motors, or capacitor start capacitor run motors, shaded pole motors. These are the mechanism of creating a positive torque at starting, okay, so that it runs. Now, you do not need often two windings when it reaches the running speed. Is it clear? Any doubts on this? Right? And you see all over one of these methods are being used for single phase motors, which you see across in your day to day life, whether you have them in the refrigerators, in your compressors, your fans, your coolers and air conditioners and so on. So, they are all using one of these methods. Okay. And there has also been the the efforts to use single phase motors for larger number of applications. Only limitation is that they cannot run beyond 3000 rpm at 50 hertz, right. That is one of the things, because your speed cannot be above the synchronous speed, and maximum synchronous speed can be at minimum pulse, that is 2 pulse at 50 hertz is 3000 rpm. Now, if any application where you require higher speeds, then you cannot use these motors, right. Now, we will take up the analysis today, but this is important. So far our discussions have been more on a qualitative basis, but that is as engineers you need to know how to analyze such machines, how to predict the performance, how to estimate its characteristics and so on. Okay. So, we will take up this analysis of single phase motors, and I will call first we have a, I will call it as method 1, which I will discuss today. Okay. In method 1, we start by maybe treating like a transformer, a single phase motor. Start from, if the rotor is at stationary speed, you can say it is like a transformer, a one winding on the stator, and you can say a squirrel cage winding on the rotor, okay, which is reflected as one winding, okay, single phase, right. And then we use this double revolving field theory as we have discussed, right. We will say how this thing can be split into half MMFs, one forward rotating MMF, another backward rotating MMF, and how they can be, for each one you can have a equivalent circuit and create the equivalent circuit and get the performance. Okay. Therefore, this we already know that flux produced by a single phase winding is sinusoidally pulsating, but not of revolving nature. It resulted two equal and opposite components, half of the amplitude of the original stator MMF wave. So, we say we will have Fs plus equal to Fs minus will be equal to magnitude of F max by 2, right. That is what we will take it as such. Now, each component behaves as an independent revolving field, okay, each revolving field, and induces its own rotor field, induce rotor currents. So, you have a forward stator MMF, okay, so you have a, let us say, forward stator MMF, let us say Fs, which is rotating. Then what will happen? it will, there are currents here. So, it will induce some currents in them, is not it, right. This will be rotor current will be induced in the bars of the squirrel cage. Okay. Then it will create an FR here. Okay. So, you will have an FR, rotor gets magnetized. So, you have Fg will be maybe Fs minus Fr, that will be the MMF here. Air gap MMF, and therefore, Fs, Fr, Fg, what are the nature of them? They also rotate forward at synchronous speed, all of them. Okay. So, you have a net forward rotating field Fg. Now, you know that Fg is varying with speed, although Fs is fixed, Fr goes on changing with speed. Fr goes on change, there will be one Fr at 0 speed, there is another Fr at synchronous speed. Okay. In fact, ideally at synchronous speed Fr is 0, no rotor current at synchronous speed. Okay. So, therefore, Fg is the one which decides the flux per pole phi g, net air gap. It is this phi g which is changing with speed, right. So, this is about the forward situation. At forward field, this is what will happen. Okay. And then we said that in the, if you go to the backward, take the same type of machine, okay, with the same squirrel cage bars, and we know that there is a Fs, maybe you call it as minus or whatever it is, that is how this is Fs, that is the potential of the stator surface, which will be half of whatever the stator MMF, because you have got only one MMF, one winding here, okay, which carries a current Is and produces an Fs. You have got Fs here, and then, but the rotor is rotating like this, opposite to this. So, there is a maximum rate of change of flux linkage. At starting, there is no problem, its reaction to forward field is same as that for the backward field at starting. So, rotor current induced due to forward field be exactly same as rotor current induced due to backward field. Okay. Now, because of this, it will have a currents in this rotor as it rotates some speed, let us say omega r, and due to this there will be Fr, rotor gets magnetized because of the rotor currents, right. When you, if it is, if rotor current is 0, rotor iron is dead, it is not magnetized. Okay. Now, at each position it has an MMF assumed at each position. Therefore, and then you have a air gap MMF here, which is Fg. What is Fg? Again will be equal to say Fs minus Fr. Agreed? Stator has assumed MMF, say it is 10 units, rotor assumed MMF 9 units, the gap MMF will be 1 unit. So, that is the magnetic potential difference between stator and rotor surface, agreed, due to the induced rotor currents in the different bars. Therefore, you have Fs minus and you may have Fr minus and you may have some Fg minus. So, Fs minus then Fr minus, then Fg minus, which causes phi g minus. What is phi g? Flux per pole, and all at what speed? What speed they are rotating? Minus ns, minus synchronous speed, not the, this is all backward. Okay. So, if you imagine at the air gap, what happens? There is a backward rotating flux per pole effectively. You do not see all the fields. For an observer, what do you see? Observer is only net flux per pole, you will see, which is rotating backwards, and that will be whose magnitude is changing with speed. Okay. This is exactly what we hammered out in the earlier couple of lectures, that assuming that the flux is constant at all speeds is a fallacy and it is not correct. Unlike in a 3-phase induction motor where flux is considered to be constant at all speeds. In a normal 3-phase induction motor, flux, air gap flux is constant at all speeds, whereas in a single phase motor, air gap flux is not constant at different speeds, because forward flux is not same as backward flux, and the magnitude of forward flux will be different than magnitude of backward flux, and they are all speed dependent. Okay. So, this is one thing which we hammered out earlier. Okay. Okay, now we will take a case when rotor is stationary, that means n is 0, that is starting, and the only one winding is excited, main winding is excited, you have one winding excited. Therefore, we said it is like a transformer with secondary short circuited. Okay. So, what we consider is you have a stator winding and you have a rotor winding which is short circuited, is not it? It is like a transformer. So, you have a current here I s, and this may be a induced currents here I r. Invariably rotor MMF will oppose the stator MMF, okay, to maintain the flux, okay, at starting. And you are aware that a short circuit, that means rotor is effectively a single phase winding at start. Then what will happen? So, you can just write an equivalent circuit, is not it? So, you say this is your voltage, stator voltage, this will be stator current, okay, and you normally have rotor current, and you have rotor resistance per phase, stator resistance, stator leakage reactance, rotor leakage reactance, and magnetizing reactance. This is equivalent circuit at S equal to 1. I think it is very obvious and you all know about it. Is it clear? So, you hold the rotor, and this can be represented by this equivalent circuit, where all the parameters are known to you. Okay. RS is stator resistance per stator resistance, there is nothing like per phase, there is only one winding. XLS is the stator leakage reactance, XM is the magnetizing reactance. Magnetizing reactance you call it as it will draw a magnetizing current IM to produce the necessary flux equal to oppose the applied voltage, right. I think you must have done it in several courses in several ways. Okay. So, we have these parameters, okay, and we have Vs, I main or Is, I will say Rs, I would prefer to have S here, XLS, XLR, E at the main or ES, XM main, and this is RR. Agreed? No problem with this revolve. This is at S equal to 1, equivalent circuit of a single phase motor at S equal to 1, right. I hope you are aware of the parameter. That means RS main is main winding resistance, XLS main is main winding leakage reactance, XM main is the magnetizing reactance, RR main is rotor resistance referred to main winding. This is important. Rotor resistance is referred to main winding turns, just like transformer secondary refer to primary turns. I hope you know what is meant by turns transformation. You create an MMF balance, okay, and create this. Okay. I think we have discussed also in when you studied with the modeling, you know how you can have a transformation of this. And XLR main is the rotor leakage reactance referred to main winding, because many times many books they sort of refer it as reactance, but it is a very misnomer. Reactance is in this it must be either magnetizing reactance or a self reactance or the leakage reactance. Okay. And I hope what is physically what do they mean, right. Resistance you have no problem physically. Leakage reactance is what? What is the stator leakage reactance? It does not go into the rotor, right. So, I think though it looks obvious, I thought it it will be necessary for you to know. If you have a, let us say this is the rotor, you put a conductor here in the slots and pass a current I, okay. Then what will it? It will produce a flux, okay. Let us say it produces a flux, and this one you call it as the magnet phi m, okay. It is the phi m which is associated with I m, which is associated with x m. This is a flux per pole, the net flux per pole, okay. It is the net flux per pole, but you also know that there are always certain fluxes, okay, which will not link, maybe it may be somewhere here, it will not go to the rotor, because here it is going to the rotor. So, there are some in the end and slots and so on. So, there are some fluxes which are produced by the I, but will not link. So, you call this as leakage flux phi L S leakage, and usually you have the leakage inductance L L S is equal to number of turns N S into I N S into phi L S by I, okay. It is the flux leakage flux linkage of the leakage flux per unit current, okay, and that invariably in air, very limited in iron. So, it is rarely saturated. In fact, this is one of the important thing. Leakage fluxes are rarely saturated, while the air gap flux or the mutual flux will have lot of saturation. Why? I have mentioned a statement. Why is it that there is saturation occurs at the mutual flux and not with leakage flux? That okay, leakage flux is not even in the air gap, it will be in the air, okay. But this has, if you look at the path, lot of the path is in iron, no? This whole thing, except for the air gap, the small air gap, lot of the path is in iron. It passes through rotor iron, it passes through stator iron, back of iron, all the things, right. If you look at the flux path, okay, if you do a FE analysis, this is what you will get, okay, right. So, these are the you applied voltage, applied current, this is the back EMF or the induced currents, okay, and induced currents will be normally given by 4.44 F into 5 M into N, okay, typically. This is the voltage back EMF, which is of course will also be equal to N d phi by dt. This is the mutual flux. So, at every instant there is a voltage which is induced in the stator winding which opposes the applied voltage. Okay. Now, you can split it up. Now, we are told you can split it up into forward flux and a backward flux. Okay. Now, that flux, that E that is produced in the winding at starting is produced by both fluxes. Okay. Even at starting there is a forward rotating flux and backward rotating flux, but both magnitude of flux are same. Okay. So, I can always say this is the flux at starting, flux per pole which is only pulsating standing, that means a magnet. Okay. This is the standing magnet, okay, which is producing the flux, right. But you also told, yes, this is equal to, I put some two small magnets which will start rotating, but at this point this is phi by 2, this is phi by 2, okay, then it will be rotating, is not it, at this ns minus ns, right. So, if this E net E is 4.44 Fn phi, I will call this will induce, this is the phi forward. So, I will have E forward will be 4.44 Fn phi by 2, E backward will be 4.44 Fn phi by 2 at start. Agreed. So, I have two but this is rotating. So, it will be inducing the voltage in that. Okay. So, we have E main forward, E main backward, and what is the magnitude of the voltage induced? It will be half of what it would be produced by the net field. Now, this is RS, XLS. Okay. So, I have split it up into this RR. Okay. So, I think I will rewrite this again for your convenience. Okay. So, we can say voltage, let us say Vs or whatever, Rs, JXLS, JXLR, RR, RR as you split up into two. Great. So, this voltage you can call it as EMF due to forward, and this voltage will be EMB due to backward. Great. Of course, this current will be IS or I main or whatever it is. So, you split it into two again at S equal to 1. Is it clear? So, EMF whatever was earlier voltage induced, EMF equal to EMB is equal to whatever earlier voltage by 2. Any doubts at this point? You just split it into two. The impedance, it is basically you have done a circuit, whatever was there what you have done is whatever was earlier air gap impedance, this is what I have made. Whatever was impedance was there with Zg looking at the air gap, I split it into 2 and I say this is Em F Em B. Now, in this case Z is same. Okay. Right. I hope till now it is okay. I have taken only a case where it is blocked condition, rotor is blocked and it is represented by the equivalent circuit and the stator winding gets 2 voltage induced, one due to forward flux, another due to backward flux. Since the fluxes are equal at starting, voltage will also be equal on the same winding. If you look at the stator winding, it produces one voltage induced, another voltage induced, incidentally both will be at the same phase. Okay. Right. Now, you allow it to rotate now at a per unit slip S. Okay. You allow it to rotate at a slip and of course, with the stator winding is excited, IS is fixed, I mean it is carrying a current IS. Now, but the rotor rotor currents are induced by forward field at frequency SF, okay, is not it. So, due to forward field you have a frequency SF, you are, I hope you know about this, right. Rotor currents will be due to this forward field will be SF and due to backward field it will be 2 minus SF. The frequency of rotor, supposing let us say n is or at let us say 2700 rpm and ns is 3000 rpm. Okay, 2 pole, then S is 0.1. No? So, the due to forward field, let us say F1 will be how many frequency? 5 hertz. Due to backward, this is for forward and backward field how much? 2 minus S, 95 hertz. So, you will know that the for a backward field it is a very high frequency currents are induced, almost double the mains frequency. So, you can imagine it will have a much higher inductances, okay, and so on. So, equivalent circuit we have to write it for different speeds, it is speed dependent equivalent circuit. Okay. So, we can write like this RS XLS XLR by 2 XM by 2 RR by 2S now, right, because then RR by 2 into 2 minus S, this XLR by 2 and I, this is the I main. Now, there is a IR, you can call it as IRF due to forward field and this will be IRB due to backward field, right. I know we have jumped in this, when we go to other steps we will see how it is. So, you are now extending from the 3 phase induction motor theory to say that this forward field is this is the forward field, this is the backward field, okay, and E main forward and this is E main backward. Now tell me, is E main forward same as E main backward? They will not be same because your forward flux is not the same as the backward flux. Magnitudes are different. Forward rotating magnet will be stronger than the backward rotating magnet, right, although both of them are rotating at synchronous speed at different directions. Okay. So, this will be an equivalent circuit under this concept of rotating field or revolving field. Okay. So, it will have forward component and backward component at a given slip. Okay. Now, you can let us say this is our frozen equivalent circuit. Then from then onwards you can forget about the field and come to the circuit. See, after all, in studying many of the electrical engineering, you always interface between the fields and circuits, okay, and fields are there in every point in space and circuit is specific to, it is a more a model, okay. Circuit is a model for you to understand. Now, then you have a, from the equivalent circuit we can determine all these quantities, you can determine what is the, when once you know the voltage and the circuit parameters, you have very easy, you can just calculate the impedance, calculate the current, you can calculate the power input, power factor, okay, at any given slip, right, you know how to do that. Now, you can imagine, you can write ZF forward impedance at the rotor is RF plus JXF, here RR by S plus JXLR, okay, which will be in parallel with JXF, okay, and ZB is RB plus JXB, where RR over 2 minus S JXLR in parallel with this, okay, in Zm. So, what we are trying to say is, you have ZF which will have JXLR, RR by S and JXM. Please at this point understand, I have not taken XLR by 2, okay. ZF is this impedance that looks from the, this is ZF is the impedance of forward field. That means impedance of the rotor from the air gap. Look at the air gap and say how will it look like due to forward field, and similarly you can have a JXLR, RR by, what do you write here, 2 minus S, right, then XM is same, not XM by 2, this you call it as ZB. So, you can call it as the forward impedance at the air gap, this is the backward impedance at the air gap, call it a backward air gap impedance, okay. So, if you root, if this is how you assume, what will be the actual circuit now, let us say Vs or so, Is, Rs plus JXLS. What do you have here now? Equivalent circuit. What do you write instead of ZF? Because I can write this, right? What will be this? What is this? Is it ZF? Huh? What is this? Huh? ZF by 2, that is why I want, okay, this is, that I am writing by different color. Please note it is ZF by 2, because my definition of ZF is not XM by 2 etc., it is this, okay, ZF by 2, right. Now, at standstill EF is equal to EB, where ZF equal to ZB. Okay. In fact, you can always say what will be EF and EB. What will be EF equal to? What is EF? Equal to IS into ZF by 2, and EB is IS into ZB by 2. Agreed? And at running, EF is generally more than EB, because ZF is more than ZB. Okay. So, EF at running is more than EF at standstill, and EB at running is less than EB at standstill. Okay. So, EF at running is more than EB at running, causing forward flux wave to increase and backward flux wave to decrease, right. Because of the rotor reaction, the forward flux will be more, okay, because at starting rotor is excited in one way, but at running for forward field rotor MMF gets decreased, and but if for the backward MMF rotor MMF gets, for the backward field rotor MMF gets increased. Is it okay? Imagine the rotor, okay. Rotor is magnetized differently, okay. So, there was a case where holding stationary, so it was excited to certain potential, let us say x. So, due to forward field that potential x will decrease due to forward field if it runs, and that potential x will increase due to backward field when it runs. Why? I made this statement. Okay. See, this rotor, it was say at positive potential x, say, okay, due to forward field, and also potential x due to backward field at start, is not it? Now, what I am trying to say is at run, this will decrease at any s, and what will happen to this? This will increase at s. Why is it so? What is the why it happens? Compared to x, because I mean I can't be every time asking the question and giving the answer myself. Why is it so? I said as it start running, rotor MMF would decrease than when it was start, because rotor current will decrease, isn't it? See, if it was carrying say 10 amperes at start, it will start carrying 9 amperes at some speed, okay, because IR is less. But due to backward field, what will happen? Rotor current will be more, because it is running at your induced EMF at a rotor. If you look at the bars, they are linking, they are having more change of flux, d phi by dt. So, IR increases. Okay. So, rotor MMF will be different. Okay. Okay. Therefore, forward and backward fields are equal at start, and then the average torque is 0, Now, running condition, okay. Now, you have got a forward, look at only the forward case now. There is a forward air gap flux, okay, right, oh gosh, and okay. Now, the backward, this is the torque, like a 3-phase induction motor, torque is produced, right. So, as far as you are concerned, there is a field in the air gap which is rotating forward, okay, and it is inducing a current in the rotor, and due to the reaction of this field with the rotor currents, it will produce. Now, we know that in induction motor, whatever the power at the air gap divided by synchronous speed is the torque. See, power going into the rotor divided by synchronous speed, this you know, due to the forward field. Therefore, what is the power at the gap? You are feeding into the gap through, feeding into the gap means getting into the rotor. You are putting some, you are transferring some power by induction, okay, and that will be I square into 0.5 RF, okay, and the forward rotor copper loss will be S times PG. I think, I hope if you recall the 3-phase induction motor theory, this you must be aware. Whatever you put in, slip times go into the losses into the rotor, okay. If you put 100 watts, if it is 1% slip, rotor copper loss will be 1 watt, okay. So, that is the kickback you will give to the rotor, it will take away its share of S, right, and only remaining it will pass on to the shaft, is not it, to be used by the outside load. Any problem? Okay. And these are the thing you are aware of. Now, due to the backward field, again the same, whatever you feed to the backward field, the power, after all there is a backward flux that induces a backward currents, there is a power into the backward field, and that power will be I square, same I, stator current I square into 0.5 RB, where RB is the resistive component of ZB, okay. And the backward rotor copper loss now will be 2 minus S times PG, not S times, okay. Now, effective slip is 2 minus S, right, okay. So, we are trying to say, if this is RF plus JXF, this is the def, okay. So, ZF is RF plus JXF, and similarly you can write ZB is RB plus JXB. So, PGF will be half of I square RF, right, and PGB will be half of I square RB, right, that is what we have said, okay. And TF was 1 over omega S PGF, and TB was 1 over omega S PGB. So, you have this torque, and net torque will be TF minus TB, okay. So, the net torque under running condition T mechanical will be TF minus TB, right, that is 1 over omega S into PGF minus PGB, agreed. So, you have given some power to the rotor through these two fields, and which will induce currents, and which will also make the rotor to experience a torque, okay. And so, net mechanical power will be whatever is, what is the mechanical power? It experiences a torque into speed, What is the speed? Speed will be 1 minus s into synchronous speed into the torque, which will be 1 minus s times PGF minus PGB. Okay? 1 minus s times PGF minus PGB. So, if you know PGF minus PGB is 100 watts, so S is 10%, so 0.90 watt will be the power output. Okay. And the rotor copper losses, after all there are now losses due to both forward field and backward field, because both currents are there in the same bars. There is a 5 hertz one and 95 hertz one, both currents are there in the same bar. So, there will be IF and IB, okay. Both will give rise to its losses, one time S times PG and then 2 minus S times PG due to forward and backward. Okay. Okay. So, we now know how to okay. So, we have all the equations now from the equivalent. If you know equivalent circuit parameters, you should be able to estimate the performance through these equations, right. You know how to calculate the current, okay. You know how to calculate the power, you know how to calculate the torque, okay. So, most of your problems are solved, okay. Only thing you need to know the parameters, okay. So, these are some of the observations that you can note down, that in single phase motor the maximum torque is not independent of rotor resistance. So, because there is a backward field also, unlike in a 3 phase machine, because of backward field, rotor resistance will have an impact on the maximum torque. Backward field absorbs some applied voltage because of backward field. If you apply certain voltage 200 volts, certain voltage is also absorbed by the backward field, only a remaining goes to the forward field, okay. And so, for remaining goes to the forward field, backward field produces negative torque and cancel the effect of positive field, because there is a dead torque will be the difference between the forward and backward torque. In single phase motor, increasing rotor resistance decreases the maximum torque and increases the slip. Why? Because if you have, because I square R loss will increase if you have a increase the rotor resistance, right. Therefore, increasing rotor resistance would also mean the efficiency will be poor, and maximum torque, the slip at maximum torque also will change, it will become at a higher slip, right. And single phase motor has lower maximum torque at lower slip, okay. Then for the same torque, single phase motor has higher slip and more losses because of backward field. Because of the backward field copper loss, this is unlike in a 3 phase machine. See, if you are having a 3 phase machine characteristics like this, you would expect the single phase one will be somewhere like this. That means, maybe here it is a maximum torque, here it will be the maximum torque here. This is 3 phase, this may be single phase, because it is having higher resistance effects, not resistance, okay, because of the backward field, okay. And volt ampere requirement of single phase motor is greater because you require to produce the forward and backward flux. So, you have reactive power requirement, you need some, it has to draw a current through this power and reactive power consumed by the backward field, okay, right. So, okay, the copper losses are higher in single phase motor, as only one phase and several must carry all the current. Copper loss is more in single phase motor than 3 phase motor. For same torque, efficiency is low and higher temperature, okay. And for same power and speed, single phase motor requires larger frame. So, if you want to make a 1 horsepower motor, you can make a 3 phase machine with a smaller frame, but for a single phase machine you require a bigger frame, okay, because you require to accommodate for the backward field, the more losses, more heating and so on. Okay. So, these are some of the basic preliminary analysis that we have covered today. The next class we will get into the concept of the symmetrical component theory, which will give you more clarity in the analysis and the findings. Okay. We will close it here now. Thank you.